The broadcast is now starting. All attendees are in listen-only mode.
All right, good morning, good afternoon, good evening to everybody who is accumulated here. Thank you so much for joining us. I am Krishna Vedula from IUCE, and I'm here to represent our partnership of IFEES, GEDC, and IUCE, where we present these global webinars on some very interesting topical areas from some various parts of the world. Today we have industry speakers from Canada. The company is Quanser, and some amazing stuff that they're doing related to self-driving vehicles, research in that area. So the topic is more flexibility for self-driving vehicles research, integrating QCar and MATLAB Toolboxes. And the presenters are Dr. Gilbert Lai and John Pineros. We have the abstract has been sent out to you, and just to get a feel for who our speakers are. On the left, we have Dr. Gilbert Lai, who's an R&D engineer, research software Quanser, and the picture on the right is of John Pineros, who's R&D engineer mechanical from Quanser. So without much ado, I'm going to hand the presentation over to Dr. Gilbert Lai and get him going. Over to you, Gilbert.
Thank you for the introduction. Let me share my screen.
Perfect.
You can see my screen?
Yes, perfect.
Perfect. Okay, so once again, thank you so much. Thanks for giving us the opportunity to present to you today. My name is Gilbert Lai, and my colleague John and myself will be giving you a little bit of a highlight of our self-driving car research studio and how we can leverage some of the tool available from our friend and partners at MathWorks through their MathWorks toolboxes. And so a little bit of an intro for our company. So we're Quanser. The name is actually stands for questions and answers. So most of what we do is fundamentally assisting our users and customers in search of the appropriate questions and the corresponding answers. So we provide products and solutions sort of with that focus in mind. And for the self-driving car research studio, it is a purpose sort of design and build platform that are validated with the goal to help our customer and users to accelerate, expand, and sustain their research and a bit of a teaching activities in the self-driving technologies, the constantly sort of evolving self-driving technologies. So what is included? What is the self-driving car research studio? The self-driving car research studio is a complete turnkey package that will allow the users, out of the box, pre-set up a set of functionalities that they can jumpstart their activities, be that research or teaching, that can help them get to the results, like get to the point that they need it to be sooner, quicker with the turnkey setup, and help them focus on more the task at hand, like the research activity or the preparing for a teaching curriculum, rather than looking at or focusing the time and energy on housekeeping item that might be typically associated with DIY, like do-it-yourself type solutions. And the main component within the self-driving car research studio is the 1/10 scale model car, which you see a picture of, that are flexible, expandable, and fairly powerful in terms of computations and what you can achieve. So focusing a little bit on the hardware side on the car, the it has an embedded processor, a very powerful embedded processor on board. It's an NVIDIA Jetson TX2 processors that is accompanied with a fairly extensive set of sensor suites with IMU, RealSense, RGBD camera, all directions camera. So we have 4 cameras facing in each of the directions, as well as a LiDAR on top to have like a all-around sort of awareness type surveillance and sensor sensing. And if the built-in extensive sensor suite is not sufficient, we also have built-in expandability and to help scale up with plenty of SPI, I2C, GPIO type general purpose IO pin and encoder connections are available to add on additional modules. The mechanical side is also fairly highly customizable. So the top mounting frame can be adjusted. You can see there's like thumbnails, like screws, so you can easily exchange or make modifications to the mechanical mounting to add modules if you needed to. And finally, because we built it as a platform for research or for student sort of centric lab environment, so we make it fairly robust, so that we understand things happen, and so we want to make it so that it's very robust, so you have a peace of mind if you want to push the envelope a little bit, or if the students are trying a few things that they shouldn't, it can take a little bit of abuse, and you can continue on with your work. And that's on the hardware side. On the software side, the car provide what we call an open architecture setup. What that means is we provide support for a lot of different platforms that you can leverage to as your development needs, and such as MATLAB and Simulink, as well as ROS or Python API is also available out of the box. So for today, what we wanted to focus on is give you a example of how we can leverage tools, functionalities available in a couple of the MathWorks toolboxes available, with an example that is a vision-based navigation example to highlight that functionalities. So without further ado, I'll pass my presentation to my colleague John to give you the rest. Take it over, John.
Thank you very much, Gilbert. Hello, everybody. I'm John, and so today we'll be going over more on the technical side for applications using the SDRS platform, and in particular the QCar. So this is more or less the agenda of what we'll be going through. So a little bit of motivation as to why visual-based navigation is important compared to how we navigate throughout our environment. We'll be looking at 2 examples using the QCar, and then at the end we'll have open floor for questions. So starting off with the motivation as to why navigating and how you perceive your surroundings is important. For the most part in robotics, one basic example is blind navigation, where basically I'm taking a scenario. This is a map of our office. At lunchtime, I like to go to a restaurant called Woodstone. And so what I want to do is figure out how to get to where I need to go. And normally as a person, as I'm walking around, I use landmarks, I use roads in order to navigate to where I'm going. But in robotics, we have access to all the sensors, but not necessarily be able to have all the algorithms necessary to fuse the sensors and figure out where I need to go. And an example would be blind navigation is if I simply have an encoder on my mobile platform and I was to simply use that reckoning to estimate, get an estimate of where I'm going in space. So as the wheels are turning, I can figure out displacement. But inherent with any platform, there might be slip. And so my estimate starts to drift. And so I can very quickly realize that if I was only to use an encoder to figure out where I'm going, even if I have a map of my surroundings, I may not actually make it to Woodstone. So with that preface in mind, what are some sensors and what are some algorithms that we can use in order to get a better idea of how that would be like? So what would I really need first? So in a previous example, I showed I have a map. So I know where I've started. But what if that map is not very detailed? Then in order for me to figure out my landmarks can be slightly tricky. So I could push that processing power a little bit further back and say, okay, well, can I build my own map? So based on my own map, I have a bias of where I am. I have a reference starting position, and then I can figure out where those landmarks are. But then the fidelity of my map is pretty much relying on how accurate my sensors are. So in order for us to better understand that, let's look at localization first. This is the first component of what could eventually build up to a full-on SLAM algorithm where I'm simultaneously localizing, as we do in everyday life, as we're walking around, we see landmarks, we have a reference of where they are towards where we are, and we build a mental map of where we are. And that way I can traverse my environment. So different examples of localization that we run through in everyday life are GPS on our cars. If you have an indoor lab, you have a motion capture system, which is analogous to a GPS. It can allow you to track a rigid body through space. On the QCar itself, I've got an RP lidar. And so this is a regular 2D lidar, gives me the estimate of all the objects in space. But for this example, we'll be looking at cameras, which can allow us to focus on specific objects in the environment. And that's how we fuse it with a vehicle model to estimate where we're going. And so as Gilbert mentioned earlier, this is just the vision sensor specific to the LiDAR, to the QCar. Having the LiDAR, this is an example here in my basement of what an RGB image from the Intel RealSense would look like. And here's another image from the CSI cameras. And so one thing you'll notice directly is the CSI cameras, there are 4 of them in the car. They have a wide angle field of view. And so this is really powerful because it allows us to see stuff on our peripheral vision, which may not be present on the RealSense. And so we can see how we can very quickly fuse that information to get a better idea of our surroundings. And so now that we've kind of prefaced what we have and a motivation as to why navigation is important, let's look at one example, which is Eyeprotags. So Eyeprotags would be analogous to landmarks in the environment, like a building. And so I can use this for self-localization as a starting point. So how does that physical setup look like? So here is a scenario in my house. I've got the QCar in front of me. I've got a box with Eyeprotags in front, and I set a reference origin. And so the intent here is I've got a vector that I know that points from my reference inertial frame all the way to the center of my Eyeprotags that I pre-measure ahead of time so I know where their location is in space. And I'm trying to find this vector that goes from the inertial frame all the way to the body of the car. And so that's what I'm trying to figure out. And so the awesome idea here is using Eyeprotags, I can go through some interesting math in order to figure out what that blue vector would actually look like. So how does this actual localization sequence look like? So I gotta figure out what my Eyeprotag information is to begin with. So how is my camera located with respect to the Eyeprotag? Then I do some QCar extrinsics calculation. I do some reference frame conversions because looking at an image through a camera, it may not necessarily be defined the same way as my inertial frame is defined. So I've got to do some conversions there to make sure that everything is in the same frame and speaking the same language. And then I do some sensor fusion with the IMU just to get a better estimate of what my displacement and what my orientation is like by combining it with the vehicle model. So now that we've figured out what this pipeline is like, first is take a step back and look at the actual camera itself. So using the computer, the image processing and computer vision toolbox, I can figure out a little bit more about my camera and how that sensor was made with the intent of being able to define a sensor model. And so the idea here is I take a checkerboard, I know the size of each of the squares, and now through some interesting math here that happens in the background, I can figure out important parameters about my camera, which are useful for this example, which allows me to get distances from images, or from the next example that we'll see, which is transforming an image to a different perspective. So camera intrinsic parameters are very important. In this example, I'm using the CSI camera. As you saw before, there's a little bit of distortion. But for the Eyeprotag example, I'm going to be using the Intel RealSense, which doesn't have as much distortion. So I can more or less remove one step, which is the debarreling of the image beforehand. So I can save on some processing. And so what this camera calibration tool can give me that's really important is the focal point of my image, the principal point, and again, what are some of my distortion parameters like radial distortion. And based on that, I can now port that over to my model to get going. Now, The next step would be figuring out what the Aprotag is. So in case you're not familiar, Ayeprotags are 2D fiducial, and they were designed by the team at Michigan University, the University of Michigan. And the idea is this is for another method of localization. So they were designed to be of high accuracy and detected at far distances. Because if you think about localization, if I can figure out a landmark from an image that is very far away, it opens up flexibility. And so I know each tag is unique because they're part of a family. And within that family and that tag, I can figure out a 6 degree of freedom characteristic about that image. And so I can fully define where I am oriented in space. So the Eyeprotags themselves hold a lot of information, which is useful for me in a robotics application. Now, how do we incorporate that within our Simulink model? So within our Simulink model, we've got a block called image find tags. And so the main idea is this block allows us to compare an ideal Aprotag, which hasn't been distorted, hasn't been skewed, and compares that with the image that we're getting. And so the idea is the rotational information, the skew information of my Aprotag is now captured in something called an X form, which defines a homography matrix. A homography matrix basically takes homogeneous coordinates that allows me to map that ideal Aprotag with the image that I'm seeing. And so I can start to build an idea of how my camera sensor is oriented compared to an ideal Aprotag. At this point, I don't know distances with respect to meters, but I can know if my Aprotag is very far away by looking at scale, or if it's skewed and how that Aprotag is located in space. So it's also very important. This block also lets me know what the corners of my Ayeprotags are. As you can see in the image, there's a couple of green pixels here that define the corners, and then there's a red pixel that defines the center. If I wanted to use that information afterwards for some plotting like I see here in my image, or if that corner information was useful for a separate application. And so here is the identification of my Ayeprotag in my image. But now I actually have to go into the localization aspect of it. And this is where more of the math and that rotation transformation occurs. So going from left to right, I know my measured Aprotag information. I did that ahead of time. That was the vector that defines the location of the Ayeprotags in my inertial frame. And now looking at the tag information, I now do a transformation that allows me to define where my camera physically is located with respect to the board. And so by doing a sequence of rotations and displacements, I can define a transformation matrix going all the way from my camera to my Ayeprotag board and back to the inertial frame. And so doing the sequence of multiplications, I can get a full vector that defines my inertial frame position of my car in 2 dimensions. Z I can take into consideration, but the car is never moving vertically. So in this case, I'm only looking at displacement in the X, in the Y, and in theta, which is useful for defining a 2D location of a mobile platform. Now, the image get camera extrinsics, what it's doing is it's actually taking into account the focal point and the principal point that we found from our camera calibration tool. So those are the first 2 matrices that you see there. And then the rotation matrix is what I'm estimating using the Ayeprotag model. And so there's a lot more math that happens in the background, but you can consider that camera extrinsics model as my overall camera model being used to figure out my location in space. And so once I've combined all of this, I also want to mention that this is just the image processing portion of our overall model. For driving our QCar around, we can see that our Simulink model has far more components. We are looking at a multi-rate system. We're looking at capturing images at 80 Hertz, for example, whereas the actual model itself could be running at an even multiple of that number. So it could be running at 480 Hertz, with the idea that we can look at processing IMU information at a much higher rate than what we're getting our images at in order to get a better estimate of what a car is doing. So we can see that we have a very complete platform here. It allows me to capture my images, to do some interesting processing, even add some logic for my indicators, whether my car is turning left or turning right, so that I can better emulate what a real car would be doing. And so the breakdown here, color coordinated, is what the intent of each of the subsystems in my Simulink model are meant to be doing. When an essentialist unit is being invoked, it means I'm looking at the actual I/O that's present on the car, which would be the camera, the actual motor, the encoder, if I'm reading that information. User interface would be I'm driving the car around with a keyboard, with my physical keyboard. So then I would have a specific block that would allow me to map my keyboard inputs for something important. And then decision planning or interpretation would then allow me to how to interpret the sensors that I'm seeing, which in this case would be the camera or the IMU. And then decision planning would then be based on what my interpretation blocks give me. What do I do with that information? And so with this Aprotag example, and when I put it all together, here's my model running. And so I can see here that I've got my image as it's processed. I can see my Aprotag in frame. I can see my car turn left. And so one thing that's curious, as the car is moving, you'll notice that the Aprotag sometimes is visible and sometimes it's not visible. And it's just an artifact of processing images. It's fairly standard. If you were to move your hand back and forth very quickly, you'll see that you don't get a still image of the hand. There's a little bit of motion blur. And so these are all things that you have to consider when you're looking at vision-based navigation. And that's why it's usually fairly powerful to combine more than one sensor, because using these estimates is very important for you to correct in case one of your primary sensors is no longer visible. In this example, when the Aprotag was not visible, I could still use my my vehicle model combined with my IMU in order to get an estimate of where I moved, and then I can recorrect that estimate because it will eventually drift. But that correction can be done with the Aprotag once it's back in frame. And so this is one example of vision-based localization. As one example for fully navigating through an environment. I have identified my landmarks. I know where I am relative to the landmark. And so another interesting topic for autonomous vehicles is lane keeping. As my car is driving, how do I figure out that lane information? And so this is the next example that I kind of want to cover. And this idea is, again, using vision for autonomous lane navigation. I can use my previous example to identify where I am, but if I don't know what path to follow, it can be very easy to drift away and also not go where my desired location is. And so now what I want to look at is what are the toolboxes that I'll be leveraging for this example. Again, because I need to get camera intrinsic information, I'll be using the image processing and computer vision in order to define that camera model, as I did earlier in the previous example. But the highlight of this application itself is the automated driving toolbox. With this toolbox, I can get a fairly powerful bird's eye view, which allows me to project my camera sensor as if I was looking on a top-down view from the car, which is very useful for identifying lane properties so that I can choose to stay in, or if I wanted to down the line, if I can figure out how to generate path to switch to a lane on the left or to the right. And so then this is also a lane keeping algorithm focused using a processed image. So we'll be sticking within pixel coordinates. And so in case you're not familiar with the bird's eye view, here's what it looks like. Again, this is an image from my basement. It's the front CSI camera. I'm now looking at a grayscale image. And now when I generate that bird's eye view, it's a tops down view. And what it can do is it'll correct any of the curves that are directly in front of me to be straight lines. They're fairly easy in this case now to identify when I want to stay within the lane. And so how does this pipeline look like in my Simulink model itself? So what I've done is I've kind of cascaded this from my bird's eye view image generation using the automated driving toolbox. And then this is now followed by the actual blocks that Quark offers, which in this case would be some lane detection using an image compare block, which allows me to just look at the edges in space. And then with some of my own logic in here. Let me figure out how to actually extract the slope of each of the individual lanes. And so what this looks like from our point of view is, if you recall the image a second ago of the bird's eye view, on the left, you see my filtered image, which is showing me my left and my right lane. I wanted to play around with different thicknesses, so I can see a very thick lane on the left side, which is very pronounced, and a much skinnier lane on the right-hand side, just to see how my algorithm would behave. And then on the right-hand side, this is now having gone through that slope detection. I now see two clear lanes, my left lane, my right lane. Where my car is headed is defined by a straight red line, and then a little pixel which defines the center of the two lanes. And so this will be powerful because what I would like to do is to control where my car is located in the center of that lane using some sort of controller. So how does that controller look like? This is a PD controller, standard for control systems, but it's a little bit more complicated in the sense that my gains are not, my proportional underderivative gains are not constant. They are modulated depending on how fast the car is going. And I found this through experimentation. And the main idea here is, because the camera is rigidly attached to the car, the faster I'm going, my image is going to shift a lot faster. Whereas the slower I'm going, the rate at which the image is changing may not be as fast. And so I can be a little bit more forgiving. And so I can correct a little bit more, or I can look at the deviation on my lanes and consider that as a more of a correcting term for where my lanes are actually sloped. The slower I'm going, whereas the faster I'm going, I may just want to consider more the slope of the lane because that may not change as much compared to how offset I am on the lane itself. And so this was all found through experimentation. I also have some a constant which is meant to modulate how fast I'm going. And so by combining now this PD controller that allows me to stay fairly close to the center of the lane, as we'll see, but also a bird's eye view, now I've got an algorithm that allows me to follow a track specified by a couple of or a set of colors. In this case, it'll just be the lane definition itself, because I'm using a grayscale image. And so now I can navigate to a desired location. So I can start seeing how I can piece my first example with my second example into a fairly powerful application. But just focusing here on how this lane keeping looks like, let's see how my algorithm behaves. So I can see on the left side the Simulink model running, on the right-hand side what my camera is seeing, and this is my car in my physical space. And I can see that the car is running at a maximum speed of 1.5 meters per second. But for the most part, I'm staying centered within that lane. And I can see on the, so if I see the four video blocks on the right side, play it again, that the center lane and the heading of my car is almost always towards the center. So I can see I've got a smooth, I've got smooth control of where my car needs to be. Going faster just means that I don't have the full ability to process the image fast enough. And so I would leave the lane, and that's how experimentally I'm able to find what my maximum speed of my car is. But this just more or less goes to show how we can use the bird's eye view as a lane keeping tool in order for me to develop a more complicated lane keeping algorithm if I'd like. And so just putting everything back together, and what we've seen in this webinar is mainly a combination of two ideas that are useful for navigation. So one, the first one is landmark detection through the environment, which I've simulated using Eyeprotags. I could use different ideas if I wanted to. That landmark could be a specific object. Maybe it's a specific color in space. Again, it would have to be defined by an ideal object so that I can figure out how my camera is rotated. Maybe I want to instrument my sensors a different way and figure out how my camera is rotated versus that ideal object in space, given an IMU, for example. But in this example, we're able to find the location of the car with respect to a reference starting position. But also we were able to see how we can enhance or leverage some of the MathWork toolboxes to get a more flexible approach for autonomous driving applications. So this is a hybrid Quark and Matrix-centric example, which just opens up another set of possibilities. I'm leveraging the computer and vision systems toolbox in order to generate what that sensor, what my camera sensor properties are. I can save that. It's powerful because I can now define my sensor at a bunch of different resolutions depending on what I would like to do. Lower resolutions maybe give me a faster frame rate, which is useful the faster I go. But if I'm more interested in picking out the details in the environment, maybe I want to do some object detection just using the camera from a bird's eye view, I may be interested in a more high resolution image, but not being acquired as fast. And so I can see what that trade-off looks like. And so this leads on to some of the future works that we could potentially look at, which is to review this lane keeping algorithm. And rather than looking at pixel coordinates, I can look at distance coordinates, because a powerful tool that the bird's eye view gives me is the ability to transform pixel coordinates on the image to an actual distance. So like I mentioned, I could look at object detection and see whether there is a pedestrian in front of me from a bird's eye view, or if there's an obstacle that is flat on the ground. It may be tricky to see from a regular view, but I can figure out what its properties are using the bird's eye view. Another thing I could do is, as I mentioned, this theme of combining sensors. So I can combine the bird's eye view from two of my sensors. In this case, it could be the Into Real Sense and a CSI camera. As I mentioned, the CSI camera has got a wide field of view, so I can use the peripheral vision from my CSI cameras, but the front view of my Real Sense being mounted higher on the car, I can see further away from where I am. And so this can be a useful starting point for a potential path planning algorithm, which now I can get a really good definition of what my lane looks like as I'm traversing my environment. And then for my Aprotag example, I could, because now I've got a definition of landmarks in my environment, I could look at combining it with my RP LiDAR. And so my LiDAR can allow me to generate a map of my environment. I can save it on the car, or I can save it on a ground station, and then I can sample my generated map as I'm with my RP LiDAR to update what my environment looks like, but then also add the location of what my Eyeprotags are. And so I can quickly start to see how I've got references for landmarks in my environment using Eyeprotags, and then what my map would look like using my RP LiDAR. And this is a really good starting point for a SLAM algorithm, because I've got pretty much points in my environment which I know are constant. So my uncertainty is fairly low. I know where they are. And if my map starts to drift, I can always correct what that map looks like when I resample a landmark in my environment, which in this case would be my Eyeprotag. And so you can see this nice set of examples and how they can morph into really specific or really complex applications for autonomous vehicles. And so with that, I'll conclude the technical talk, and then I can open the floor for some questions. And thank you very much for listening.
Okay, wow, that's fantastic, Gilbert and John. I love the concept of having a little QCar and doing research on it so that you learn more and more about autonomous cars, and then perhaps using that as a teaching and research tool in academic institutions, right? Is that the ultimate purpose of what you're doing, is to set up these kinds of labs in different institutions?
That's correct. That's what Quanser is about. We provide a lot of the in-lab equipment to help as a development and validation platforms. It's sort of sits in between the theory and simulations versus a field test, real life size deployment.
Mm-hmm. Oh, it's fascinating because it covers so many interdisciplinary aspects of various curricula that are built into this whole program. And so it really is a nice comprehensive way for students to learn about various skills that they need for the future technology as well. So let's open this up for comments. In the meantime, Hans has joined us. You want to say a few words, Hans, welcoming our friends from Quanser?
Thank you very much, Krishna. Dear Gilbert and John, I don't think I've had the privilege to meet both of you in person, but I just want to thank you for this very thoughtful presentation. our partnership, IFEES, GDC, and IUCE, working closely with Krishna, is very important with Quanser. It goes for a decade and it has deepened, and so I'm very pleased that you're able to communicate with our global community through this kind of presentation. I was just talking with Paul, your executive director. You will be engaging with us in November during our global conference, in which we obviously bring together faculty and leaders, deans, but very important is the engagement of students. We have a global student forum, and I know students listening to this will be very excited. So we're finding a way to engage you, continue to engage you in a thoughtful way, not only regionally, but at a global level. So on behalf of our three communities, I thank you very much for your very, very thoughtful presentation. Peace be with you, and please stay safe. Thank you kindly.
Question about, do you currently, are you working with any institutions in Canada, like one of the, like McMaster or some other place where you're doing some of the stuff as part of the curriculum in some universities anywhere in the world right now? You started that already?
We have actually engaged a lot of institutions worldwide, and obviously we're based in Canada, so it's a lot of Canadian institution is our partner that we work with. In particular, as you mentioned, in McMaster, we have a close working partnership to help them virtualize their curriculum at the start of this, actually just started this past couple of weeks in the fall term. The tools that was used it's not specifically to the QCar. So the QCar primarily at this moment is we launched it earlier this year as a research studio sort of a tool. So we are constantly looking, as sort of you mentioned, Quanser has been a global partner with engineering applications, and we are constantly looking for partnerships and opportunity to develop or co-develop teaching sort of materials and curriculum to help enhance student engagement in that regard. So we do have another product called the QBot that has a mobile robotics curriculum, and we are looking at incorporating some of that with the QCar as we move forward as well. A lot of the current engagement we have is what is our, given the pandemic situation, virtual lab support. So what we call the Quanser Interactive Lab, which have a lot of our equipment that has been virtualized to help still provide a hands-on, meaningful, and high fidelity engagement through the simulations, but at the same time giving realistic sort of response to help engage the students in their pursuit of the knowledge and experimentation.
Great. We have a few of our friends from around the world who I'm sure are familiar with Quanser from various places that they've been at and met your folks. Let's hear from them. Let's hear some comments, questions, etc. Okay. So Felix says, in your lecture, it was mentioned degrees of freedom was 6. For statistical estimations, will higher degrees of freedom improve the accuracy of prediction in your model?
It could be, depending. Well, redundancy is a good thing, but what we are looking for is the 6 degrees of freedom locations and position orientation in space. So having additional, I wouldn't say additional degrees of freedom is a measurement, but additional data points to help with the sensor fusion process would certainly help improving the estimate accuracy.
Mm-hmm. So if universities wanted to collaborate with you, what would be the next steps that they would have to do? How would they go about approaching you guys?
Oh, I think we can share our contact information, or we're always like info@quanser.com, I believe is the general information, and then you can cite the how you heard about us, or you've listened to this particular webinar, and then we'll definitely contact you, reach out, and have the follow-up discussion.
Okay. Other comments, questions coming, guys?
So I'd like to take this opportunity from Quanser and thank you again for providing us a platform, be able to talk to you today. It's wonderful. As mentioned, we have been a very close partner, and we are constantly looking for collaborations.
Okay, great. So I guess we don't have anybody else who has any questions or comments. They're all saying thank you for the very good presentation. So Hans, you want to close the webinar?
Again, just many thanks. I think the number of attendees is very excellent, and we continue to build on this. And we can help facilitate, introduce you also to some of our close friends in some of the different universities in all of the continents. So thanks for taking the time. It means a lot to us. We value it deeply. Thank you kindly, and all the very best.
Okay,
Thank you. Likewise.
Thank you, John. Appreciate your time and your excellent presentation.
Thank you very much.
Everybody from around the world, have a good evening, good morning, good night, whatever. Okay. I guess there's the last question that comes in. How can I be part of this project as a college student? We have several students in here, so I guess they would have to look for some ways to associate themselves with a university that is doing work with you, right?
We do work with colleges and institutions worldwide as well. So reach out to us. We're constantly eager to listen to and hear back from any feedback or potentials like collaboration opportunity, like I said before.
Could you put up your slide with an email ID maybe? Yeah, somewhere along, might have been there, or one of your email IDs. And we can always send it to them, but try to just put it up right now. Might help. Or
Do we have that on the slide, John?
No, we unfortunately don't have that on the slides.
Okay, just repeat the email,
just
gentlemen.
repeat it, and my colleague Sridhar will broadcast it. So just spell it out.
Okay.
So the email is just our name. So for me is gilbert.lie@quanser.com.
Okay, Gilbert.lie. Sridhar, you got that? Gilbert.lie at Quanser.com.
Yes.
Gilbert.lie. So that's gone out. Okay, and for John?
Perfect. And so for me, it would be the same thing. So my email is john.pineros@quanser.com. Fantastic.
John.pineros@quanser.com. Fantastic. Okay, so that's come out in your chat box. Sarthak, you should be able to see both their email IDs, and you can reach out to them. And you're the future of the world. So reach out to them and find out how you can get involved with this question and answer. It's a fascinating name of the company, Quanser, and question and answer. Good luck.
Yeah.
Take
Thank
care,
you very
and
much.
everybody.
Perfect.
Yeah, thank you.
Thank you very much for your time.
Bye-bye, everybody. Bye-bye.
Stay safe.
Bye.